Welcome back to Chapter 4. In Chapter 4, we are going to be looking at applications of derivatives. So far, we know how to find these derivatives, but what can we use with them? So this is where we're going to be finding out more about that. In this section, we're going to be looking to see how derivatives can help us find extreme values of functions. I know just a couple years ago, a teacher asked me if there was an algebraic way of finding a maximum or minimum of a function that was beyond a quadratic, like of a cubic or a quartic or something. Um, and I thought about it for a second. I thought, well, no, we don't need that because we just use calculus, and that's going to be way easier than anything that's algebraic that would do the same thing. So let's take a look at what we're going to do here. Our learning targets for today. We're going to use a given graph to find the extreme values of a function and where they occur. We're going to use analytical models to find the extreme values of a function where they occur. That's what we're going to focus on. A graph, you're just looking at a graph, and it's pretty easy. We're going to solve applications involving extreme function values of functions. We're going to determine whether statements about local extrema are true or false, and we are going to prove statements about the critical points and extreme values of functions. So the first thing we're going to look at is the absolute extreme values, which are also called global extreme values. Global just because it's the extreme value of the entire system, of the entire graph, of the entire thing within the domain we're looking at. Um, and so our definition of an absolute extreme value um, is this. You can read it. It basically says that the absolute maximum is the biggest thing the graph can get to. The absolute minimum is the smallest thing a graph can get to. So, for instance, if we have, say, a quadratic, we're going to look there. A quadratic has an absolute minimum. The absolute minimum is right there. That's the lowest thing that this graph is going to be. If we cut the domain, let's say our domain here is going to be from 0 to this point. So we're here, that's about the same. That would be the absolute maximum if that's the domain. Generally speaking, a quadratic either has an absolute minimum, like we have here, or if it's an upside down quadratic, it would have an absolute maximum. The only way it has both is if that domain does get limited. Something like a cubic function, all on its own, has neither an absolute maximum or an absolute minimum. Now again, if we limit the domain, so we're only looking at a chunk of it, then it will have absolute maximums and minimums. Something like a sine or cosine graph does have absolute maximums and minimums because we're going to get this 1, negative 1, 1, negative 1. Those are the biggest and smallest things that a sine or cosine graph could be. I mean, granted, yes, we could do a vertical stretch and get different numbers there, but either way, that's still going to be the absolute maximum and absolute minimum. That happens or happens an infinite number of times if we keep going, but it has both types. We have the extreme value theorem. And what the extreme value theorem says, if f is continuous on a closed interval, a to b, then f has both a maximum value and a minimum value on the interval. So what this says is it has to be on that closed interval ab. So if we take this cubic and we close it, that's our interval AB, it will have an absolute maximum and an absolute minimum value because it has those endpoints. So if we're looking at a restricted domain, there will be a largest point, there will be a smallest point. Now it might be shared, like in the sine and cosine, like there might be a number of times it hits that, but the absolute maximum or minimum is the y value. So for a sine or cosine graph, the absolute maximum is 1. It hits it a bunch of times. The absolute minimum is -1. In this case, on the cubic here, we've got the absolute maximum would be this point here. The absolute minimum might be that point, but it looks like it's going to be that point right over there. So it has an absolute maximum minimum. It might be at an endpoint, it might not. We're going to be seeing how we can find these in just a minute. So those are the absolute maximums and minimums. That's the global extreme values. Oh, I did not fade that in. So in a minute, we're going to talk about a stationary point. But we're looking at the local or relative extreme values now. Those are the relative maximums and minimums. And what those are, here's the definition that really doesn't help all that much. It's not really English. A relative maximum is a point that's higher than all the points around it. A relative minimum is a point that's lower than all the points around it. Like the summit of Mount Baker is a relative maximum. Is it the tallest thing in the state? No, but it's the tallest thing around. When you're standing at the summit of Mount Baker, everywhere you look, you're looking downhill. A relative minimum would be standing in a valley. It might not be the lowest point on Earth, but everywhere around you is higher. So that's what the local extrema are. So as we're looking at these, here we have a graph that we're cut. So we're going from A to B. We have a local minimum. There's this. This is not the lowest point. The lowest point is over here, which is a little bit lower. But this point is lower than everything around it. We're looking up both sides. Here's another local minimum because it's the lowest thing around. We don't care what's over here because that's outside of the domain. Everything around it is above it. We also have some local maximums. That one, it's not the highest. The highest one's over here, but everywhere around it, you're going downhill. So that's a local maximum. The absolute ones, that's also a local maximum. Like it still counts. It's the local and an absolute. So the absolute ones also count as the local. Same thing with this absolute minimum. It also counts as a local minimum. But so when you look at a graph, it's really easy. You're just looking to see, oh, it's right there and it's right there. On graphing software, graphing calculators, it'll tell you what that value is. Most of the time you'd be looking at a graph and it's by observation. You can see, it's like, oh, hey, that's going to be the biggest point right there. But how would we find it algebraically? Well, what happens at these local values? And we've talked about this already before this year. And what happens is you have a vertical or a horizontal tangent line. Well, horizontal line means it has a slope of 0. The slope is the derivative. So when the derivative equals 0, you're going to have a local maximum or minimum. But what about this one right here? Let me erase some of my circles there so we can actually see what it looks like. That does not have a derivative of 0, but it has a corner, it has a cusp. It's somewhere that the derivative does not exist. So what all of these things are is they're called critical values or critical points. And a critical point is where the derivative equals 0 or the derivative does not exist. Those points are values where we can have local maximums or minimums. Not always. For instance, if we have y equals x cubed, the derivative there, y prime equals 3x squared, is going to equal 0 when x equals 0. But if we graph this, remember the graph of y equals x cubed looks like that, where yes, the derivative does equal 0 right there, but then it keeps going up. It's not a maximum or a minimum. These give us the places where it can be a maximum or minimum. And so the critical points are where the derivative equals 0 or the derivative does not exist. Now, the stationary point is where the derivative equals 0. So we have some extreme values. How we tell what the extreme value is, what the absolute maximum or minimum is we're going to find all the places in an interval where the derivative equals 0 or the derivative does not exist, and we're going to find the y values at all those places. And also the endpoints, because those are the places it could happen. This process is called the candidates test. Is the name of it super important? No, but if the assignment or test or quiz tells you to use the candidates test, you need to know what it's talking about. That's just this. So if we look at a function, we're going to find a few different things. We're going to find the critical points, the local extrema, the extreme values of the function on -2 to 6. So that's going to get us that domain restriction. And then we're also going to see where it's increasing and decreasing. Because we don't actually have to find the values to see if it's going to be a maximum or minimum point. We're going to see that here in just a second. So the very first thing we need to do is we need to find the derivative of this. So this is just a simple power rule problem. So f prime of x is going to equal 3x squared minus 12x minus 15. So it's a polynomial, so it's not going to, the derivative won't not exist anywhere. So we just have to figure out where it equals 0. So we're going to factor this. We can factor 3 out of it. We have x squared minus 4x minus 5. And then we can factor that. Be x and x, -5 and plus 1. And so this will equal 0 when x equals 5 or -1. We're going to do a sign table for this. So a sign table, as we've done this before when we were looking at if the velocity was increasing or decreasing, it's the same basic idea here. So we're going to plug in some values. So we can plug in a number less than -1, say like -3. We're going to have a -3 minus 5 is a negative number, -3 plus 1 is a negative number. A negative times a negative is a positive. So we'll have a positive slope. And then a number in between -1 and 5, like 0. -5 times 1, that's a negative number. And the number bigger than 5, 10. 10 minus 5 is positive, 10 plus 1 is positive, positive times positive is positive. So what we have here is we have a positive slope, goes to 0, goes to a negative slope, goes to 0, goes to a positive slope. If I was sketching that, the positive slope going to 0, going to a negative slope, going to 0, going to a positive slope. When we have a positive slope going to a negative slope, that gets us an absolute or a local maximum. So we have a maximum. Oh, so let's see, the critical points were x equals 5 and -1. We have a maximum at x equals -1. And then from a negative slope to 0 to a positive slope, that gives us a minimum. So we have a minimum at x equals 5. So we didn't actually have to graph the equation for that. Now, if we were looking at the that one from before, where it was y equals x cubed, and so y prime was 3x squared, that gave us a critical value of 0. If we plug in numbers less than 0, we square it, it's a positive. Greater than 0, we square it, it's a positive. And so it doesn't actually change sign there. Maximums and minimums, local maximums and minimums happen when the derivative changes sign. So we go from positive to negative, it's a maximum. We go from negative to positive, it's a minimum. So now for extreme values from -2 to 6. So now we have this -2, and we have the 6. So 6 will be bigger than 5, and negative 2 will be smaller than negative 1, but we don't know if it's going to get above or beyond these values. And so this is where the candidate test comes in. Sometimes it's possible to tell if it's going to be the absolute maximum or minimum just based on what you have, but in this case, we don't know. So what we're going to do is we're just going to plug them in. So we're going to have x, we're going to have our critical values, negative 1, negative 5, and the endpoints, negative 2 and 6. And then f of x. We have to find those actual values of the function, not of the derivative of the function. So we plug in negative 1, we get negative 1, negative 1 squared is 1, so negative 1 minus 6 is negative 7, plus 15 is 8, plus 2 is 10. Plug in, no, that's not a negative 5, that's a positive 5. Why didn't anyone correct me on that when I wrote it down? Come on, people. So we plug in 5. 5 cubed is 125. 5 squared is 25 times negative 6 is negative 150. Negative 150 plus 125 is negative 25. Minus 15 times 5. 15 times 5 is 75. So we have negative 25 minus 75 is negative 100 plus 2 is negative 98. Now you might be doing this with a calculator or on paper, not necessarily in your head, but it gets negative 98. So that's this value and this value. Now we need to find the endpoints. So we plug in negative 2. Negative 2 cubed is negative 8. Negative 2 squared is 4 times negative 6 is negative 24. So we have negative 8 plus negative 24 is negative 32. And then negative 2 times negative, that's plus 30. So that gives us negative 2 plus 2 is actually 0, which is less than 10 because we knew that that was going to be less. And then plug in 6. 6 cubed is 216 minus 6 squared times 6. That's 6 cubed. So we have 6 cubed minus 6 cubed. Goes away. Nice. Negative 15 times 6 is going to be negative 90 plus 2 is negative 88, which is a little bit bigger than that 5, so that works out there. So now we want the extreme values, the absolute maximum minimum. For the absolute maximum, we just have to think what number is the biggest. Hey, 10 is the biggest number here. For the absolute, so this is the maximum. For the absolute minimum, what number is the smallest? Negative 98 is the smallest. So the absolute max is 10, and it happens when x equals negative 1. The absolute minimum was negative 98, and that happens when x equals 5. So sometimes, like here, it says find the extreme values. Find the absolute maximum minimum. That's 10, negative 98. Sometimes it'll say something like, where does the absolute maximum or minimum occur? In that case, you need to know the x value because that's where it occurs. To be safe, you could say the absolute maximum is 10 at x equals negative 1, and same thing for minimum. It's negative 98 at x equals 5. Now, it asks, where is it increasing? It's increasing when the slope is positive. So it's positive here until we get to 0. So it's increasing from negative 2 to 0. So we have the square bracket on the negative 2 because it has a positive slope at negative 2. We have a parenthesis at 0 because it's neither increasing nor not 0, negative 1. I'm such a noob. All right. Negative 1, because that's where the derivative equals 0. So we have that parenthesis there because at negative 1, it's not increasing. It's increasing up until that point, but at negative 1, it's 0, so it's neither. And then it's also increasing over here. So and a parenthesis again, so 5 to 6, and 6 gets a square bracket because it is still it's still increasing at that value. So that was some. Let's find some more extreme values. So let's find some extreme values of a different function. This one is f of x equals 1 over the square root of 4 minus x squared. So we're going to have to go through kind of the same steps. First, we're going to need a derivative. But before that, I would rewrite this as 4 minus x squared to the negative 1/2. Negative because we're in the denominator, 1/2 because it's a square root. Now we can use the power rule with chain rule. So f prime of x is going to be, we'll have a negative 1/2 times 4 minus x squared. Subtract 1. Negative 1/2 minus 1 is negative 3/2. Where's my pen? There we go. All right, then times the derivative of the inside. 4 is nothing, so minus x squared will be a negative 2x. We can rewrite this. Negative 1/2, so we'll have negative. That 2 will be down there. We'll have a 4 minus x squared to the 3/2 down there. And then negative 2x up here. The negative and negative will make it positive. The 2's can cancel. So we end up with just a positive x over 4 minus x squared to the 3/2 as our derivative. We need to know when this equals 0. Well, it equals 0, a fraction equals 0 when the numerator equals 0. So numerator equals 0 at 0. So x equals 0 is a critical value. Now, we don't have a domain restriction here in the problem that is stated specifically. However, if we look back to the original equation, we have that square root. So first of all, we can't have 0 in the denominator. Secondly, the square root can't be negative. So this 4 minus x squared has to be greater than 0 because it's inside the square root. I'd say it would have to be greater than or equal to 0, but the equal to would actually give us 0 in the denominator, and that's also bad news. So it has to be greater than 0. So we can add the x squared over. So 4 has to be greater than x squared, square root, both sides. So plus or minus 2 has to be greater than or less than x squared. So 4 has to be greater than x squared. X is going to have to be in between negative 2 and positive 2. Because when we square each of those, we get 4. If we square stuff less than those, like in between those, we get something less. So here is our domain restriction. So we want to find extreme values. We're just going to have to plug these values into the equation. So we have x and f of x. So x could be negative 2, it could be 0, it could be positive 2, because we have our critical value and we have our endpoints. Plugging those into the original equation, if we plug in negative 2, we're not going to get a value that's going to be nice. Because we're going to get divided by 0, because it can't equal negative 2. But we can plug in something really close to that. And that would give us, if it's a maximum or minimum, but it won't actually equal negative 2, so we could always get something just a little bit closer. So it's going to not give us these values, but it will go off to infinity there. And if we plug in 0, we get 1 over square root of 4, which is 1/2. And so this would be an infinity, this would be an infinity. So if we graphed this, it would actually look like thinking about the curvature on this one. Curvature on this one is going to be positive. It's going to go up to infinity that way. It's going to have like a angle, or actually it's around there because it is 0. So it's going to look like that, where we have these asymptotes here. And so we have a minimum right here at x equals 0. So our extreme values, x equals 1/2, f of x equals 0 is the minimum. Except no, backwards. God, it's 2 mistakes in one video. That's bad. All right, so our minimum is 1/2, and then there is no maximum. Well, but the absolute value theorem, or the extreme value theorem, said that there has to be a maximum and a minimum. That's if it's on a closed interval. This is not a closed interval. This is an open interval because it can't equal 2 or -2. This is this interval. In order for the absolute or the extreme value theorem to hold, it would have to be like this, because here we can get closer and closer to -2. Like, so whatever value we choose, it's not going to be there. There's always one that'll be a little bit bigger than that. And that's our infinite problem there. So I think we have one more. We have a piecewise function here. So we want to find the extreme values of this. If we graph this, which is always nice to see kind of what the graphs are going to look like. We've got a quadratic there, and then we have a line. So we're going to have maximums and minimums here. We're going to have those. Those are going to be relative or local maximums and minimums, because we're going to keep going negative and we're going to keep going positive. So in general, this one will not have an absolute maximum or an absolute minimum, because we're going to keep going. If we decided that we had to limit the domain, we could have those, but with no limit on the domain, with no interval there, it's going to keep going maximum, minimum. There's no absolute maximums or minimums. So what we need to do is we need to find our critical values. Our critical values are going to be this one, which happens when the derivative of the quadratic equals 0, and it's going to be that one, which would be the intersection of the two pieces of that piecewise function. And so if we want to figure out where the derivative of the quadratic equals 0, we would take that quadratic and we would find the derivative. So that'll be 0 to equal to 5 goes away, so we have -2 multiplied, so 4x. So that equals 0 when x equals 0. And the other one is when x equals 1. It's a good idea to check to make sure that those derivatives aren't the same there, because if they are, that's not going to be a maximum or minimum at all. It has to have a corner, which means the derivatives are going to be different. So if we plugged 1 into this derivative, we would get -4. If we plugged 1 into the derivative for the bottom one, well, the derivative for the bottom one is 1, so the derivative would be 1. -4 does not equal 1, so there is in fact a corner there, which we're seeing as we're looking at the graph anyway. So we could do a sign chart for this, because we know there's not going to be any absolute ones. We don't have endpoints, but we have 0 and 1. So our sign chart, below 0, we'd have to plug it into the top one because it's less than or equal to 1. So a negative number, let's say -2, we plug it in. -4 times -2 is 8. That's going to be positive, which, based on our graph, that's a positive slope. That makes sense. In between 0 and 1, Again, we're looking at that top equation. So plug in 1/2, -4 times 1/2. It's a negative number. So we go from a positive to a negative and a 0. This is going to be a maximum. And then when it's above 1, well, the derivative of anything above 1 is 1, which is going to be positive. So we go from a negative to a positive. That's going to be a minimum, as we can see. So the maximum happens when x equals 0. The minimum happens when x equals 1. We see that on the graph. Now, it wants the extreme values. That means we have to find what those actual y values are. So we're going to need to find f of 0, and we're going to have to find f of 1. So the local max, f of 0, we plug in 0. 5 minus 2 times 0 is just going to be 5. And then the local minimum is, we plug in 1 into either of them because they actually intersect, but we could make sure it's continuous, plug it into both. 5 minus 2 times 1 is 3. 1 plus 2 is 3. So this is going to be 3. So the local maximum is 5. Local minimum is 3. So with that, that is how to find those extreme values on our graphs. We can look at them graphically. We can look at them analytically, which is using the equations, finding the derivative, seeing where it's 0, where it doesn't exist, and the endpoints. People always forget about the endpoints. And then seeing which is the biggest. That's our maximum. Which is the smallest. That's our minimum. So with that, I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.